Okay, shall I start?
Okay, it's our pleasure to introduce Alexander Pushnitski, who will make a great lecture. Please begin, start.
Thank you very much, Sasha. Thank you. Okay, so I just have to warn people that if there are any experts in the audience, at least the first hour will definitely not be for them. It will be purely introductory. So my target audience are mainly people from St. Petersburg, whose background is mathematical physics, spectral theory of for differential operators, rather than Hankel and Tuplets operators. So I will basically just introduce Hankel and Tuplets operators, and then I will start talking about their spectral properties. Okay, so let me first start with some motivation or introduction. Okay, so what are Hankel and Tuplets operators? So let me first start by introducing them just as matrices. So we consider everything in L2 of Z plus. This is our basic Hilbert space. So Z plus in my book is 0, 1, 2, 3, etc. Okay, and so Hankel operators and Tuplets operators are operators given by the following, by matrices of the following form. So suppose we have a sequence AN, a double-sided sequence.
Sasha, I'm sorry.
You don't see the screen. Okay. What happened? I don't understand. Let me just. Whoops. Something is not working. I don't understand what is. Okay, let me do the following. I will try to, I will do something else. I will join Zoom and in a second capacity from my tablet. Maybe then it will work better, yeah? Okay, so just give me a second. I'm shocked because before that it was all working. So give me a second. So I need to put the meeting number. Okay, so I think I've joined. Now I need to do one more thing. Just excuse me for a moment, because there is a sound feedback. I need to plug something in. Okay, so now we'll try to share the screen from here. Share screen. Okay. Now I go to here.
It's now okay.
Great, thank you, Roma. Excuse me for this. I don't understand what happened. I give lectures every week, and this is the first time this is happening. Okay, all right. So you can hear me, you can see the screen, right? Perfect, thank you. Okay, so let's start. So once again, what is the easiest way to introduce Hankel and Tuplets operators? As infinite matrices in this little L2, Okay, so we suppose we have a double-sided sequence. Let's call it AN. Then associated with this sequence, we introduce Tuplets operator. This is the operator of the following form. You put A0, A0, A0 on the diagonal. Then you put A1, A1, etc. Here you put A-1, and so on. So the constant elements are on those lines. Okay. And then you associate with it a Hankel operator. This is the following infinite matrix. Here you put A0, here you put A1, A1, A2, 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 and so on. So the constant, so elements are constant along those kinds of diagonals. Okay, so this is the easiest way to introduce Hankel and Tuplets operators as infinite matrices. So in other words, here I can write it in this form. And here I can write it in this form. So these are our operators. So the aim of the course, the aim is to describe eigenspaces of Tuplets operators and Schmidt subspaces of Hankel operators. So by the way, Schmidt subspaces of Hankel operators is the same as eigenspaces of gamma star gamma. So as we shall see, these are the natural questions to ask rather than the other way around, rather than, for example, Schmidt subspaces of Tuplets and eigenspaces of Hankel. At least for this, we have more or less definite answers. So to describe them, I will describe their structure. So to describe them, I will have to move from the picture of little L2 to the picture of Hardy space in the unit disk, because this is where we have a reasonable description. And so my next aim is to give you an easy introduction to the Hardy space. I'm sure some people in the audience don't need this, but I'm assuming there are some PhD students in the audience, so I will briefly introduce Hardy space, and then I will talk a little bit about how to realize Hankel and Tuplets operators in the Hardy space, a little bit about the spectral properties in general, and then I will start moving towards description of the eigenspaces. Okay, so that's the program. So let's talk about, yeah, first of all, maybe I should just briefly mention what are eigenspaces and Schmidt subspaces. So eigenspaces, okay, so because I have it on my plan, but this will be very brief. Eigenspaces and Schmidt subspaces. So if we have, let's say, a bounded operator in a Hilbert space, then, well, everybody knows what an eigenspace is. Eigenspace is a kernel of A minus lambda identity. So we will say that lambda is an eigenvalue if this kernel is non-zero. So what about the Schmidt subspace? Schmidt subspace. So we will, if there is a number S, which we will usually call singular value, and then we associate with this value S the following subspace. This is my usual notation for this. I don't know if it's so standard, probably not. So this is the kernel of A star A minus S squared identity. Okay, and so if this subspace is non-empty, it means that there exists a non-trivial pair, let's call them Xi and eta, in our Hilbert space, such that A Xi equals S eta and A star eta equals S Xi. This is called the Schmidt pair. So I will also mention, we will need it in the future, that it is easy to see that A star acts from this subspace to this subspace. I hope I'm not confusing the order. And no, I am confusing the order, right? It's A. A is acting from here to here. This is A. So, and A star acts in the opposite direction. Okay, so that's all I need to say about eigenspaces and Schmidt subspaces. I do not assume these things to be finite dimensional or my operators to be compact. This can be anything. Okay, so now let's move on to discuss Hardy space. Okay, so Hardy space. So Hardy space can be thought of in 3 different ways. So the first way, it's not really Hardy space, but it's a sort of a set of coefficients of functions in the Hardy space. But nevertheless, this is just L2 of Z plus. Okay. Secondly, one can think of it as space of functions on the unit circle. So T in my notation is a unit circle on the complex plane. And in this case, it can be naturally thought of as a subspace of L2 on the unit circle. So in this case, if you think of it in this way, then the elements of the Hardy space are functions Grisha, I think it's you. Okay. So, okay. So if we think of a Hardy space as a subspace of functions on the unit circle, then we just think of them in this way. So these are functions given by these expansions. And by the way, if something happens, if you don't see my screen anymore, shout, because I'm looking at my notes, so I cannot follow everything at the same time. Okay, so so these are the set of functions like this, and of course our condition for these functions to belong to the Hardy class is that this sum is finite, and this sum will give us the square of the norm. And finally, we can think of the Hardy class as the set of functions inside the unit disk. So in my notation, D is the open unit disk in the complex plane. And in this case, it's actually the same thing, the same representation, but we just think of Z being not on the unit circle, but in the unit disk. So each of these representations has advantages, and each highlights different aspects of the theory. So typically one works interchangeably in the second and third representations. So to go from the representation on the unit circle to the unit disk, you have to take analytic continuation of the function inside the disk. To go from the last third representation to the second one has to take the boundary values of the function analytic inside the unit disk to the boundary, and this is not such a trivial process. There are theorems to this extent that any functions in analytic in the unit disk satisfying certain growth conditions has boundary values, but we will not go deep into this. Okay, so now let me mention a few aspects of these different representations that we will need in the future. Yeah, so first of all, some notation. So in all of these representations, I will use, oops, just something happened here. Sorry, I've pressed the wrong button. Now I think I've stopped sharing. Let me do it again. Sharing screen. Okay. So so in all of these representations, I will use this to denote the inner product. And this to denote the norm. And now let me mention a few points related to this representation as functions inside the unit disk. So let me start by pointing out that if we take the inner product of f with 1, this is the function which is identically equal to 1, then what happens is that all the Taylor coefficients in this expansion die apart from the first one, okay? The zeroth one rather. And the zeroth one is exactly the value of our function at 0, at the point 0, at the center of our unit disk. So we can write this as f of 0, okay? So more generally, if we take a function, if we define a function, let me call it like this, u alpha of z equals 1 minus alpha bar z, where alpha is inside the unit disk, then this is what is called the reproducing kernel of the space. Reproducing kernel, which means that if you take an inner product of f with u alpha, you recover exactly the value of your function at alpha. So you can do it simply by looking at the expansion. So u alpha of z, if you expand it as like this, then this becomes simply just if you write down the inner product with respect to with this function, then you'll see that this is exactly what happens. Okay, so now let me mention a couple of operators that we will need in the hard disk space. So the first operator is not really in the hard disk space, but onto the hard disk space. So this is the projection P from L2 on the unit circle to H2 on the unit circle. And this is simply the projection that sends. So if you have a function in L2, then this is of course given by its Fourier series. So the projection P simply kills all the terms with the negative indices. Okay, so this will be a very important operator for us. The second important operator, maybe even more important, is the shift operator. So let me move to the next page. So, okay, shift operator. So probably the first way you meet the shift operator is in your beginner's course in functional analysis, where it acts on a little L2. So you can think of S being acting on a little L2, and then it maps this sequence to this sequence. Okay, so it shifts the whole sequence to the right and replaces the first element by 0. This is why it's called shift. So alternative way of thinking of the shift operator is, I will still denote it by the same letter S, as something that's acting on the hardest space. Doesn't matter where you think of the unit circle or the unit disk. So you simply map f of z to z f of z. And this clearly does the same job if you think of the Fourier coefficients. Okay, so importantly, we will also need the adjoint operator. So this is called the backward shift. So if you think of this as a operator in L2, then this is then what it does. It maps this to x1, x2, etc. So it shifts everything to the left and it kills the first element, the 0th coordinate. Okay, so alternatively, you can think of this acting on the hard space. And then you can see that you can write it like this. So here I'm thinking of the unit disk rather than the unit circle. Okay, so f of z is mapped into this combination. So this is our backward shift. Okay, so both operators are contractions. The first one is an isometry. The second one is has a non-trivial kernel, one-dimensional kernel. And generally speaking, the spectral theory of this operator, for example, the theory of understanding of what are the cyclic elements for these operators, what are the invariant subspaces for these operators, and so on. So the spectral theory of these operators is one of the central topics in analysis in the hard space and more generally in analysis. Okay, so now I want to discuss Tuplets operators in more detail as operators acting on the hard space. Okay, so let me move on. Okay. So suppose we have a function, let me call it A, same letter as I used before, but for a different purpose. So suppose we have a function A, which is a bounded function on the unit circle. So we will call it a symbol. Okay. So then we will define Tuplets operator on the Hardy class as follows. So I take a function f from the Hardy class, I multiply it pointwise by A. So this multiplication is done on the circle. So by the way, here you will see here, and then what follows, you will see that we all the time we jump between these two pictures of Hardy class as a space of functions on the unit circle and the space of functions inside the unit circle. So when we want to talk about things like zeros of functions, then we need to think of functions defined on the unit disk. When we talk about the multiplication operation, so like here, for example, we are trying to multiply a function A, which is only defined on the unit circle, not inside the unit disk. Then we are talking about operations on the unit circle. Okay, so so here I'm talking about the unit circle picture. So we take a F, which is in H2. We multiplied by A. So this, of course, after this multiplication, this function is no longer in the Hardy class, because if it only had non-zero positive Fourier coefficients, now it has it all became messed up after this multiplication. But then we projected back onto Hardy class, and so we call this this operator Tuplets operator with the symbol A. Now let's compute the matrix of this operator in the standard basis of H2. So by the way, I forgot to say that the standard basis in H2 is simply the powers of Z. Okay, so let's compute the matrix of our Tuplets operator in the standard basis. So what we get is, first I will write this calculation in great detail, because maybe for some of you this is new, and then I will be faster in what follows. So we write it like this. So here I'm simply writing the definition of P, of my Tuplets operator. Now I notice that on the second position, the function is analytic. Okay, so if I move this P to the right-hand side, I don't need it, right? Because PZM is ZM. So I can remove this P because of this. So I have a ZN, ZM. Now I'm thinking of this as in a product in L2. Okay, because H2 is a subset of L2. And so this can be written as an integral over the unit circle. And now, so here is the Lebesgue measure. And so now, oops, something happens again with this thing. Okay. So now I write this as Z M minus N bar. And so what we see, what we get is simply the Fourier coefficients of A of Z with the index M minus N. So this is exactly the Tuplets matrix, the matrix that in the very first slide today I called Tuplets matrix. So we see that if we define the Tuplets operator in this way, in the standard basis, it will have a Tuplets matrix. So we are really talking about just two different representations of the same object. Okay, so first of all, then I need to say a few things about the spectral theory of Tuplets operators. First of all, boundedness. So TA is bounded if and only if A is in L infinity. So I've started from the bounded symbol, and so it's clear that if the symbol is bounded, then what is our tuplets operator? It's a combination of multiplication operator and the projection. So the norm of multiplication operator is, of course, the same as the L infinity norm of A. And so it should not be surprising that we have this estimate. On the left is the operator norm of the tuplets operator. On the right is the norm of A as an element of L infinity. But in fact, we have equality here. In fact, we have equality. This is not difficult to check at all. And moreover, if you try to take A from unbounded, then the tuplets operator will turn out to be unbounded. Okay, so this is a very nice, satisfying relationship. Okay, so the second point is kind of algebraic. So let me phrase it like this. So an operator TA is tuplets, or let me maybe, okay, like this. So T is a tuplets operator. If and only if it satisfies the following commutation relation with the shift operator. Okay, so this is called as a Brown-Halmos theorem. So in the one direction, it's relatively easy. You just take a tuplets operator and check this property for it. Let's do this because it's a really nice and simple exercise. So we simply take TA S F. So here put a star G. And we rewrite this as TA S F S G. So this becomes P of A S F SG. Now SG is in the Hardy class, so we can remove this P by the same trick. We just move it to the right hand side and then it disappears. So this becomes A S F S G, and now I consider this as an inner product in L2. And so then this S on both sides, this is just multiplication by Z on the unit circle. And it cancels, right? You have Z and Z bar, it cancels. And so in the end, you get A, F, G in L2. And now I can put the projection back because G is again in the Hardy class. So I get P of AF G. And this is just TAF G. So I've checked on, in terms of the quadratic forms, this identity. So in one direction, this is kind of easy. This is this simple calculation. In the other direction, it's less easy, but not so difficult either. The important thing is just to observe this, to notice this, and you can prove it. It's not so difficult. So in other words, if you work with tuplets operators, you can take a point of view that you don't need to worry about the symbol. You just work with an operator satisfying this abstract algebraic relation. And if this is all you need, then you just prove theorems like this without specifying what the symbol is. So in fact, we shall see that the main result about the structure of eigenspaces of tuplets operators that I will prove in the end of this course will be proven exactly like this. All we will need is this commutation relation. Okay, so now let me discuss spectral properties of tuplets operators a little bit. Yeah, maybe first some simple example. simple example, if we have a tuplets operator with the symbol which is just Z, what is this then? This is P of Z F, and we don't need P because F is already in the Hardy class. We multiply it by Z, so it's still in the Hardy class. So this is ZF. So this is just SF. Okay, so TZ is just S. So let's look at another one, TZ bar. So this is P of Z bar F. And so it's not difficult to see that this is exactly S star F, right? So Z bar, if you think of this as an operation in L2 on the unit circle, it shifts everything to the left, and then P kills the zeroth element which appeared, which went below the line, which went to the left. Okay, so this is S star F. So we have these two nice examples, shift and backward shift. So now let me just mention, without too many details, the a few spectral properties of tuplets operators. Okay, so first of all, so first of all, maybe even before saying this, so we know that it's easy to see that to take the adjoint operator, we just need to take a complex conjugate, right? And so in particular, the class of self-adjoint tuplets operators, this is exactly the class of operators with real valued symbols. This is a nice, interesting class, and there is a very deep theorem due to Marvin Rosenblum. Let me check the year, I think it was beginning of the 60s, if I'm not mistaken. Yes, it was 1960. So he proved that if you have a real valued symbol, then the spectrum of the tuplets, corresponding tuplets operator, is purely absolutely continuous. Purely absolutely continuous. So no eigenvalues, no singular continuous spectrum. It's a completely non-trivial fact. Next observation, which is totally trivial, is just the identity is a tuplets operator with the symbol 1. Okay, and so because of this, if I'm talking about this operator, so if I'm aiming to study the kernel, then this is the eigenspace okay, so I can write it like this. I put this identity into the symbol. And so in other words, once again, the kernel, the eigenspace of this operator is the kernel of another tuplets operator. So studying eigenspaces, studying the structure of eigenspaces of tuplets operators is the same as studying the structure of their kernels. You just have to change the symbol. Okay, next point. Let me just check my notes. Yes, so in general, if you have a symbol which is not real valued and not continuous, something quite general, then the study of the spectrum of Tuplets operator is a very difficult problem. But for some reasonable classes of symbols, you can make much progress. So in particular, if the symbol is continuous, then it's very well known and very well understood. So if you have a continuous function on the unit circle, then the essential spectrum of the corresponding Tuplets operator is precisely the set of values of your function. Okay, so the essential spectrum is the set of lambdas where this operator T minus lambda identity is not Fredholm. So imagine that you have your symbol, and right, and this is the what you get if you follow, if this is the image of the unit circle by your symbol. Okay, so then everywhere on this line, the spectrum, you have the essential spectrum, and then inside you may or may not have, so this is not essential spectrum, but you may or may not have a kernel of the corresponding operator. So what do I mean? So I mean that the kernel of this operator is non-trivial if and only if the winding number of this is negative. So what do I call by the winding number? I pick a point somewhere inside this circle, and then I see whether the how many times I go around around the circle when the variable z goes around the circle. So a of z describes some loop in the complex plane, and so I'm wondering whether this loop altogether has where the argument of a of z makes a full circle or not, and in what direction, and I count this. Okay, so if this winding number is negative, then the kernel is non-trivial. That's the description. So in my picture, actually here the winding number is I think positive here, right? And positive where there's the red dot, and negative here where's the blue dot, I think, if I'm not mistaken, something like this. Okay, so this is a kind of a very brief introduction into the spectral theory of Tuplets operators. Now I want to move on to Hankel operators. Any questions so far, by the way?
Sasha, I have a question.
Yes.
About the result of Rosenblum. So suppose A is just 1, then the Tuplets operator is identity operator.
Thank you. Thank you. You're absolutely right. I forgot to say this is the only exception. So if the symbol must be non-constant. So if you have a non-constant real-valued symbol, then the spectrum is purely AC.
But well, suppose the symbol is real, and we consider the spectrum, and in particular we cannot have any eigenvalue, because
that's right. That's exactly right.
But then we study eigenvalues on the next several lines, or I don't understood something.
No, but on the next several lines we do not assume A to be real valued. So this, of course, this is, sorry, I didn't say this. So here we are talking about real valued symbol.
Yeah.
After this, the symbol is no longer real valued. It's just some complex valued symbol.
Yeah, so and this is consistent with this result about essential spectrum, for example. Yes,
Exactly.
if it's
Exactly.
real value, then the winding number is just 0.
Winding number. Well, so we don't define the winding number in this case. We only define it if lambda is not on the image of A, but nevertheless, sort of intuitively, heuristically, you are right. It's you know, the image is of A is just on the real line. So it's so. By the way, you know, I think it's a very nice problem to try to understand what happens if you have a. Let me draw here. If you have a if the image of the symbol is like this, right, some sort of oval around the real axis, and then it shrinks to become real, right? It would be a very nice exercise or research problem to try to understand what happens in this limiting regime, you know, when non-real symbol becomes real. Because here, you know, we have real kernel, true kernel, but then it kind of shrinks to nothing.
Okay, thank you.
Right. So now let me, in the same spirit, sort of very quickly, very superficially, talk about Hankel operators. So Hankel operators on the Hardy space. Okay. So I will denote, initially at least, I will denote Hankel operators by gamma, following Adamian, Arov, and Crane. So gamma is probably because of, in Russian, it's called Gankel. Okay, that's my guess. That's, I think, why they denoted it like this. So, Gankel, yes. So, so now let's look. What is this Gankel operator? So suppose we have a symbol U. So there are two kind of schools of thought. So some like to have this symbol to be analytic, and some want to be just a bounded function on the unit circle. So let me assume that it is analytic and in fact bounded. So H infinity is the set of all bounded analytic functions in the unit disk. So then I will define gamma U, the Gankel operator with the symbol U, as follows. So this will be P of U dot JF, and JF of Z will be F of Z bar. Okay, so let's check that this, so I take F of Z and then I replace it by F of Z bar. In this case, F was analytic, now it becomes anti-analytic. So it means that only its negative Fourier coefficients are non-zero, with the exception of zeroth Fourier coefficient. The coefficient in front of constant will still be there. Then I multiply it by U. So now, of course, the coefficients are all over the place because U is analytic, JF is anti-analytic, and then I project it back onto the Hardy class. So let's check that this definition gives us exactly the Hankel matrix as I defined it on the first slide. So we write gamma U Zn Zm. So this is, so we get P U. So this J, this flip operator, makes Z bar N of Zn, and here I get Zm. So again, because Zm is analytic, I don't need this P, I remove it. So then it becomes U Zn bar Zm. and I can consider this as an inner product in L2. And then I do the same thing as for tuplets. I move Z bar n to the right-hand side. I get this, and so this gives me u hat of n plus m. So it's exactly the Hankel matrix as I defined it on the first slide. Okay, so just as for one remark is that I could start with U not necessarily analytic, but for example, bounded on the unit circle, and the result would be the same. But observe the following, that the Hankel operator doesn't know anything about the negative Fourier coefficients of U, because here in this formula, I only get n plus m, and both n and m are non-negative. So it only cares about the non-negative Fourier coefficients of U. So if I define Hankel operator in this case, then it only depends on the Fourier coefficients of U with the non-negative indices. Okay, and so sometimes it is convenient to allow you to have some non-trivial negative coefficients, but in most of what I'll be doing, I'll be thinking of U being analytic. So then the symbol is unique for the operator, right? Otherwise, the symbol is not unique. You can add to the symbol anything with negative Fourier coefficients, and the operator will not feel it. Okay, so now for tuplets operator, remember that we had a defining commutation relation. So for Hankel operators, there's the same story. So yeah, maybe I should first say a few words about boundedness, because so far I didn't say this. So just as for tuplets operators, if U is bounded, then it follows that gamma U is bounded, but the converse is not true. So you can actually add you can have small singularities of this U and weak singularities of this U, and the operator will still be bounded. So the correct correspondence is U is in the so-called BMO analytic class if and then. This is an if and only if condition for gamma U to be bounded. So I will not even define this BMO-A class because it will play no role in what follows. This is just sort of for completeness, for your information. So these functions of the BMO-A class, they may have sort of weak logarithmic singularities. So this BMO-A class, in some sense, it sits between L infinity and all LP. Okay, so it is smaller than all LP classes, but it's a bit larger than L infinity. Okay, now what about this commutation with S, commutation with the shift operator? So it turns out that gamma is a Hankel operator. If and only if we have the following commutation relation. Okay, so again, it's a simple exercise to check it, that if gamma is a true Hankel operator, then this is true. In the opposite direction, it's a little bit more difficult, but again, not something terribly deep or difficult. And so again, you can study Hankel operators simply by looking at this relation if you wish. So, and in fact, this is mostly what we will do in the last part of this mini course. Now, just for information, I will mention a couple of other points about the structure of Hankel operators, the spectral structure of Hankel operators. So for Tuplets operators, by the way, I forgot to mention that for Tuplets operators, well, this was sort of implicit in what I said, but Tuplets operators are never compact unless they're zero. Okay, so if a Tuplets operator is compact, that just means it's a zero operator. So for Hankel operator is no longer true. So for Hankel operator, you can have compact operators and you can have non-compact operators. So let me say a few things here. If U happens to be continuous, okay, so if U is continuous, well, analytic or not, this is not so important here. So if U happens to be continuous, then gamma U is compact. If U has a jump discontinuity, this makes our operator immediately, it makes it non-compact. In fact, it gives gamma non-trivial, some non-trivial AC spectrum. Now, a more basic theorem is a Kronecker's theorem. From 1880s, in fact, from the 19th century. It says that gamma U is finite rank if and only if U is rational function. So because we think of U being bounded on the unit disk, it means that this rational function must have zeros outside the closed unit disk. So U is a factor ratio of two polynomials, and let's say they have no common factors, and the polynomial downstairs, the Q polynomial, shouldn't have zeros in the closed unit disk. Okay, I will take a break in a minute, but let me just give a simple example that is an illustration to Kronecker's theorem. If we take the reproducing kernel, then it's easy to check that the corresponding Hankel operator is actually rank 1. So let me give it as an easy exercise, maybe for the break. And now let's take a break and continue in half an hour. Okay. Any questions?
Everything is perfectly clear.
Thank you, Roma. So far. Okay, I will speed up a little bit in the following.